This is Juno 6 and it's question 4, part A. State the principle of superposition as it applies to two waves of the same type which arrive at the same point in a medium. So the principle of superposition, and this is something really you should learn, is that the total resultant displacement is equal to the vector sum of the individual displacements. So that means just that you add up the size of the displacements at that particular time, and if they're plus or minus, you must take that into account of the two waves. Two waves of the same type arrive at a point and produce complete destructive interference. State two conditions for this to occur. So they must have the same amplitude if they're going to completely cancel each other out. And then they must be at 180 degrees out of phase or in antiphase, so that a trough is arriving at the same time as a crest and they are completely cancelling each other out. Part B, in figure 4.1, S1, S2 and S3, there's S1, S2 and S3, are three sources of sine waves of the same frequency and phase. The amplitude of S2 is fixed, but the amplitudes of the other two sources may be varied at will. Source S2 is midway between S1 and S3. P is a point on the line perpendicular to S1 and S3 through S2, in other words, it's across here. Under certain conditions, the waves arriving at P from the three sources may produce complete destructive interference. State what these conditions are and explain how they result in complete destructive interference at P. So we just have a wee look at what's happening and maybe make this a bit bigger. From S, if I just draw a wave, and we'll make sure that this is a crest that's arriving here, so I'll go backwards. If I just draw a wave like that. Okay, and then if I have, I'm going to draw two waves from S1 and S2. And what I want for complete destructive interference to occur over here, there must be a trough arriving from this direction here. So I'm going to have a trough here. Okay, and then over here, and I want another trough arriving here, like that. Now, those two troughs should add up to give you a total displacement which is equal to this displacement, and they should cancel each other out. Also, these waves here should have travelled farther. So if this was a triangle, you'll see that this is a hypotenuse of the triangle, and therefore this distance must be slightly longer than this distance here. So these waves from S1 and S3 have travelled slightly longer. If they have travelled slightly longer, they have to be half a wavelength out of phase. So the total distance that they've travelled is half a wavelength more than this wave in the middle, so that they're half a wavelength out of phase. In other words, you get a crest arriving from this, but troughs arriving from these two green ones here. So we're going to try and write all that down. So the first thing is, what are the conditions for complete destructive interference? And so the conditions for complete destructive interference is that the waves arriving from S1 and S3 must be in antiphase to S2. And that works because S1 and S3 have travelled further than the waves arriving from S2. Secondly, for them to completely destructively interfere, S1 and S3 must arrive at the same time. They must be in phase with each other. So S1 and S3 must be in phase with each other. And they travel equal distances. The next thing then, and these are really the conditions. The conditions are that the sum of the displacements of S1 and S2 must be total, give you a total of the displacement of S2. Sorry, S1 and S3, that is. So if we look at that again, if this is, say, we'll say half a centimetre, the green one's half centimetre trough, and this green one's half centimetre trough, the total displacement of that trough is 1 centimetre, and that must equal the total displacement of the crest, which is 1 centimetre there too, the purple one. And then the last one, and this is that the difference between the distance S1P and S2P, i.e. the extra distance that S1 has travelled, must be half a wavelength. And that's written as n plus a half times lambda. So the number of wavelengths that it's out of phase, it doesn't matter how many full wavelengths it is, it's a half wavelength that's important. So it must be at least half a wavelength. And if you were to write that down for S3, of course, it's exactly the same. S3, that distance minus S2, is also the same, n plus a half wavelength, and that has to be true, otherwise they won't destructively interfere. So that's quite a lot, and it's quite a nasty question there, and maybe quite difficult to get full marks in that question. So that would be worthwhile learning this off, conditions for destructive interference. Of course, if it was constructive, it would all be opposite. These waves would have to be in phase. They would still have to travel in equal distance. The sum of the displacements doesn't necessarily have to be the same to have complete destructive or constructive interference, but it may be that. And then whenever you take these two distances away, you get a whole number of wavelengths difference. In other words, that they're in phase. So if I just put the pen over that, if you took that distance there away from that distance there, you can't see that. If you took this distance here away from that distance here, the difference should be a whole number of wavelengths.